Okay. I actually made the light-dependent reaction video before this one because I wanted to have this drawing. I think it's going to help explain some things. So the first, I'm calling this one the foundations of light reactions because there's a couple of things that you need to understand in addition to the stuff that you need to understand for photosynthesis, specifically for the light-dependent reactions. For example, light. What is light? How does the energy transform? Because we know the energy is not created nor destroyed, but it simply is transformed. How does it get transformed in this light reaction? What do the pigments actually do? In one of the other videos, I talked about what a pigment was, but what do they do in the light-dependent reactions? So this is the foundations of light reactions, and we're going to use this picture to get us started. So the first is I can explain the energy transformations that occur in the light-dependent reactions of photosynthesis. All right, so where the energy starts is up here at the sunlight. Okay, so we're starting with radiant energy, which is sunlight. Okay, and the energy is then going to go into the chemical energy of, energy of the electrons. The electrons are going to carry it. Then we're going to use that energy, that chemical energy of the electrons, we're going to give it to these little guys, and we're going to use it to create a concentration gradient. Well, the concentration gradient is the type of potential energy. I'm going to start using big E for energy. That's the abbreviation. I don't use it very often, but I'm running out of room. So then we now have this potential energy. And then lastly, we're going to use that. Well, part of it we're going to keep chemical. So if we're looking at this line, we have the chemical energy of electrons that becomes the chemical energy of NADPH. So we could kind of branch off there. So chemical energy of NADPH, so that's one. So radiant to chemical would be this part. But then the other part is radiant to chemical to potential to mechanical, because when it falls through, this guy actually starts spinning. That's kinetic energy or mechanical energy. So we'll go with kinetic since that's the energy of movement. That's less specific. And that is ATP synthase. And then lastly, we use that to create a bond. So that's chemical energy. And that is with ATP. So I kind of had to go off to the side. So it depends on what part of the light reaction, but for the most part, we are taking radiant energy, and we're going to end up with chemical energy. I can explain light as radiant energy. All right, so that's physics. All right, I don't do physics. So what I'm going to show you is what I looked up. And so radiant energy is basically the energy of electromagnetic waves. It does travel as something called a photon. So light actually has what we call particle duality, or the dual nature of particles. It can travel as waves and photons. And so a photon is just a tiny package of energy. And waves, of course, you know, like that. So I looked up electromagnetic radiation. That didn't really help me, but you can pause it and read that if you want. And so I thought, well, what is it I really want to know? Well, I want to know, where does electromagnetic radiation come from? When we talk about radiant energy and we talk about it comes from the sun, where is it coming from in the sun? And that might be a deeper dive than you want to go. But anyway, so it's basically radiation. Okay, so you kind of know what radiation is, that is created when some part of an atom is caused to move. So when that part, and in this case it's the electron, that's why it's called electromagnetic, when it's when the electron starts to move, it's going to create some magnetic fields and some electric fields. And those are going to, I don't know what the traveling at right angles to each other, I don't know what all that means. But anyway, that movement, that little bit of kinetic energy is bundled in this little thing. And so it travels through space, kind of shaking and moving. And it's going to deliver that energy to whatever, if it's absorbed or reflected, or, you know, we talked about that with light transmitted. So anyway, if you care about that, you can Google it more, you can go into it more. But basically, radiant energy is the energy that radiates out from the sun. It's due to a lot of the different chemical reactions that are going on in the sun. There's a lot of fusions and fissions and all kind of nuclear stuff going on in the sun. And so it's all of that's releasing radiation, and that's what light energy is. It's that radiant energy coming from there. All right, the next one is I can explain the role of pigments in photosynthesis. Pigments are found in the photosystems. So you can see I put in chlorophyll. We know it's chlorophyll because it's green. And their job is to absorb a specific color of light. Chlorophyll A absorbs red, chlorophyll B absorbs blue, so those are the two main colors that plants need and love. And they then take that energy from that light. So red is a real kind of slow energy, blue is a higher energy. And so they take that energy from that light and they give it to the electrons. And there's a special pair of chlorophyll molecules in this photosystem that can do that. So there's a bunch of chlorophylls. Most of them are just absorbing, but there's a special pair of chlorophyll that aren't absorbing. They're collecting, they're almost like a funnel, and they're collecting all of that energy and funneling it to the electrons. So that's the role of pigments. I can differentiate among the different types of pigments. So there are two main pigments, and those are chlorophyll A and chlorophyll B. Chlorophyll A is going to be absorbing primarily red. It does some other colors too, but the most is red. Chlorophyll B is blue. We can remember that because B for blue. And then we have some accessory pigments. And accessory pigments, if you think about what an accessory is, makes your outfit look better, your earrings, your scarf, your shoes, your purse, all that good stuff, your wallet, your belt, if you're a guy, whatever, a watch maybe. And so accessory pigments are going to help the main pigments do their job. So we've already said that chlorophyll A and B prefer red and blue light. That's just what they're good at. They cannot absorb green, neither one of them. And that's why plants are green, because they reject most of their green light, because these two guys say, sorry, I can't use you. So the accessory pigments, phycobilins, which are red in color, xanthophylls, which are yellow, and carotenes. You probably heard of beta carotene. It's a vitamin. Carrots have a lot of carotene. Sweet potatoes have a lot of carotene. All of your orange vegetables have a lot of carotene. But these are the colors that they are. So it's not that phycobilins can use red. Phycobilins are red, which means they don't use red. They reject it. So they're absorbing greens and blues and those kinds of things. Xanthophylls, they cannot use yellow. They're rejecting it. Carotenes cannot use orange. They're rejecting it. But the good news is they all kind of overlap, and they're absorbing some of the colors that the other ones don't absorb, as well as green that this can absorb. So between these 5 pigments, and I'm sure there's some others floating around in there too, some other accessory pigments, you're getting a lot of the sunlight. Still not getting as much green, and that's why plants are green, because they're rejecting a lot of that. But you are getting some green absorption with these guys down here. They all do the same thing. They all absorb light energy, and they funnel it. Actually, all of them funnel, even chlorophyll B, funnel their energy to, or the energy they absorb to chlorophyll A, and chlorophyll A is the one that gives it to electrons. So chlorophyll A is absorbing, but it's also giving it to electrons, and it's collecting all of the energy that these guys absorb and giving it to electrons. And then lastly, I can describe the purpose of a photosystem. So we have 2 photosystems, photosystem 1 and photosystem 2, and they're named again because of the order they were discovered. So photosystem 2 is first in the process, but it was discovered second. So that's why this is photosystem 1, because it was discovered first. A photosystem is simply a transmembrane protein. So it's a protein embedded in the thylakoid membrane that contains a reaction center. So it contains what? Contains chlorophyll. Lots and lots of chlorophyll. I just drew a couple, but there's a ton in there. And that chlorophyll, and it also contains these accessory pigments. They're absorbing. Okay, so they're constantly absorbing light. And then there is a special pair, and I don't really have room to show it because it's too tiny, but there's a special pair of chlorophyll kind of right there in the middle, chlorophyll A, that are collecting all of that energy from all the other pigments, and they're giving that energy to electrons. So the purpose of the photosystem is to absorb that sunlight energy, that radiant energy, and to charge up those electrons with that energy, to pass that energy to the electrons. So those are kind of the different foundational things about light-dependent reactions. If you have any questions about any one in particular, or all of them, or 2 of them, or whatever, just let me know, and I hope that helps.